research in peer-reviewed journals and presents at international science meetings. Everyone welcome Benjamin.
Thanks so much. I'm delighted to be here. It's fun to have a new bunch of students because the semester at BYU just ended. They get out earlier than everyone else because they don't have spring break, because nothing good happens with college students in spring break. So they got out early, but now I'm missing teaching. Now I get another chance. Chris and Miriam, thanks for the introduction. I remember when Chris in particular reached out to inquire with my ability and interest in participating. I'm delighted. That's Chris and Miriam with Keto Chow. Guys, thanks so much. I'm delighted to be here. It really is a fun opportunity to share some of what we do in my lab. And I'm from right around here, right? BYU is 30 miles away. I have an active research group there, and it's a lot of fun. It's a wonderful place to be as a scientist, in part because the students that I get to work with are really quite extraordinary. When you get a bunch of early 20-year-olds who commit to not drinking and having premarital sex, they're very, very productive. They get a lot done in the lab. They're very productive. So it's a very productive lab, and I'm glad for that. All right, so by way of disclosure, I'm a co-owner in Insulin IQ and Best Fats, coaching and supplements, and then I'm a consultant with an international supplement company called Insulin. Now, my focus on mitochondria is, well, in fact, that's the focus of my talk. Chris, I'm just going to shift this a bit so I can see and be a little more mobile. Hopefully I don't want to plug anything. You're familiar with, Amy's mentioned mitochondria. In fact, Amy, what a delightful talk. I have just so enjoyed learning more about brain glucose hypometabolism. And it started with you. I'm just delighted to hear that. So we need mitochondria. Mitochondria are essential, as Amy noted, in energy production. While it is true that there is the potential within the cell to produce energy for the body, for the cell to use and get done what it needs to do, to work, most outside of mitochondria, most of the energy production within the cell, the overwhelming majority will occur within the mitochondria for the cells that have it. We know of documented instances, pathologies in humans, where disordered or disrupted mitochondria play a big part of the development or the etiology of that disease. And I have them listed here. And of course, many of these are not inconsequential. Sarcopenia being the loss of muscle, dementia, loss of brain function, cardiomyopathy being the loss of the functioning of the muscle of the heart, very distinct from just heart disease in a general sense. So a lot of bad things can happen when the mitochondria aren't quite up to snuff. So we need healthy mitochondria for healthy function. We have been, several of the speakers, and I'm delighted, again, to be here, and it's a little sort of funny to be the concluding speaker. I'm amazed that not this many of you have stuck around all day. But several have mentioned the word metabolism. And as a person who actively studies metabolism, I'm always a little weary on how it's used. Not that it's been used incorrectly, but essentially metabolism is the sum of two general processes. It is the balance of the catabolic processes that are involved in breaking things down. For example, nutrients. Primary nutrients being lipid and glucose. So the catabolic processes are taking something complex like nutrients, and the anabolic processes are taking simpler things and building things out of them, like glucose in the form of via gluconeogenesis or glycogenesis, lipogenesis in forming lipid, and then just even the synthesis of protein. So we have here then catabolic processes breaking things down, anabolic processes breaking things up. Now, just as there is kind of a connection on the top of this metabolic circuit, there's a connection on the bottom, and that is now the actual production of energy. I do kind of beg your pardon. I hope this talk doesn't get it won't get too technical. You're going to follow it wonderfully because you're all pretty informed and quite clever. But it's definitely more of an applied talk, but I promise it'll get interesting, or more interesting in a second. So ATP is the molecule. When we speak about the cell making energy or the mitochondria making energy, that's what we mean. That is the energetic we always call it the energetic currency. It's what the cell is using to buy something, to get something done. When a muscle is contracting and relaxing, that's the main work. It's an obvious sign of cellular work. ATP is literally what's allowing that to happen. So that's cellular energy. When we talk about that, we're talking about ATP. ATP is a product of metabolism, or breaking things down. ATP can also be used and is used in anabolic processes, and we're building things up. It costs energy to build things up. Now, on the catabolic side, I want to introduce this other concept. And you've already heard me talk about some of this before. We also have the production of metabolites, and that could be something as obvious as, say, lactate. Remember, humans, mammals, animals don't make lactic acid. Okay, anytime someone's saying my muscles, my legs are sore, I need to elevate them and clear out the lactic acid. No. So you may as well say that they're sore because unicorns are poking the muscles. Not bacteria, we don't make lactic acid. But lactate could be an example of a metabolite. And then I have that little flame indicative of the production of heat, which in fact is a consequence of any chemical reaction. Now, one other distinction when we look at metabolism in this paradigm that I'm giving you is the location within the cell. In particular, the catabolic processes tend to occur within the mitochondria, at least to a degree, and in some instances to a large degree, whereas the anabolic processes are occurring outside of the mitochondria in the area known as the cytosol. I'll come back to that concept in just a minute. Now, as we look at this metabolic paradigm, this circuit including catabolic events and anabolic events, you can see that we have created, at least the way I presented it, a circuit, a circle. And how does the cell prevent itself from going in this vicious cycle of building things up just to break things down? Could you see why that's a problem? That would be very inefficient, and the cell would abhor that inefficiency and in fact wouldn't do it. So I've created this circle, and what actually determines which event is in charge? Is it catabolic catabolism or anabolism? And it has everything to do with the hormone insulin. Insulin will determine which metabolic event is predominant. In other words, which metabolic event is actually happening. Are we catabolic or are we anabolic in general or at the level of the cell? I would encourage you, as time would allow, to read some of these delightful studies from a man named George Cahill. When I'm talking about insulin being this key controller of metabolism, that's not my line. I'm stealing this from George Cahill. And he's referring to insulin not only as controlling metabolism, but also being the hormone that indicates the fed state. What's important about that is, of course, if someone has high insulin, it might be high even when they haven't eaten. It's like their body is stuck in a fed state. In contrast, if you can maintain a diet and lifestyle where insulin is low, then it's like even when you're eating, your body is in a fasted state and benefiting from that in all of the myriad ways. So insulin is key here, and it looks a little something like this. As insulin is elevated, it is promoting anabolism. If insulin is low, it is promoting catabolism. That's what I mean by the arrows being the way they are. So high insulin is anabolic to the cell, telling the cell to build things up or at least not break things down. If insulin is low, it's signaling to the cell, hey, you're free to start breaking things down. Like my kids, after we've cleaned up the room, it doesn't last for long. Things get catabolic very quickly in my home. And that's okay. At least I tell myself that's okay. That's my limit. My kids joke, just recently, my daughter read a book where the protagonist has like a rally, a war cry. And so all my kids have made their own little war cries. And one time they were saying, what would Dad's be? Dad's war cry was, pick it up. That is absolutely true. I say that probably more than anything else. Dave Feldman says I love you the most. I say pick it up the most. Okay, then maybe after that I say I love you after they pick it up. Okay, now I introduced another thing you couldn't notice because I was distracting you. I put glucagon up there. I've already spoken about insulin and glucagon, and they are two halves of a coin, or the yang to the yin, glucagon to insulin. They are both relevant to anabolic and catabolic processes. If insulin is the main anabolic hormone, you could say glucagon is the main catabolic hormone. And some might make the case that there are others that are more reflective of catabolic effect, and I would disagree. And I would say, prove me wrong. So in this case, let's now introduce ketogenesis. Ketogenesis, of course, is a really nice sounding name for just the liver being told to make ketones. This is a catabolic process at its core, where the liver, the mitochondria within the liver, are taking fatty acids, and I just have indicated there, mentioned as lipid, and it is breaking the lipid down. Indeed, it's breaking it down at such a high rate that there's almost, as I often describe it, here's the cell's energy needs, and the body, because insulin is low, the mitochondria within the liver almost can't help but breaking down more fat than it needs for energy. And then this little excess becomes an exhaust valve, if you will. There's a way to spill that extra energy that's being created off, and that's the production of ketones. And that's reflective of what I've talked about previously with regards to ketones inducing this state of being able to waste energy. And as Dr. Nally mentioned, it is allowing the person to be in a metabolic advantage and yet maintaining the integrity of the laws of thermodynamics. But I'm getting a little distracted. Quit distracting me. So here with catabolism, I'm mentioning fatty acids being broken down. That's they're broken down into this molecule acetyl-CoA. In fact, that's, I think, whatever next talk I give somewhere else, I think I'm going to focus a whole talk on just acetyl-CoA. It really is at the it is a keystone molecule that represents this nexus of catabolic processes, like, for example, the breaking down of lipid, and then anabolic processes. For example, acetyl-CoA can go on to become cholesterol. Now, what I'm about to say here is that if insulin is low, there is so much production, there's only two options to acetyl-CoA. It can go into this, and I mean it, it can go into the citrate cycle, or it can go into ketogenesis. And so why doesn't it go into the citrate cycle? It's because the citrate cycle gets so full that it stops allowing acetyl-CoA to go in. Basically, the cell is saying, I don't need any more ATP. And the citrate cycle exists to create molecules to go on to make more ATP. So the cell is saying, we've reached the energy load. We don't need any more. The only other avenue is the production of ketones. Even cholesterol, everything else, any other thing to do with acetyl-CoA requires that insulin be elevated. Insulin is not. It's either a citrate cycle or it is ketogenesis, so we take the ketogenic route because the citrate cycle gets full because there's plenty of energy. I hope that's making sense. If it's not that important anyway. At least all of this is introduction, so I haven't even gotten into my real topic yet. So the relevance of ketones, any cell in the body that has mitochondria, which essentially means every cell except the erythrocytes, the red blood cells, will greedily gobble up ketones as fuel. The liver, in fact, isn't. That's also an exception. It makes them and doesn't use them. As mentioned a moment ago, when Adam described ketones as kind of hormones almost, where they are signaling molecules. Indeed, they are signaling molecules. And regardless of what else is happening in the body, if a person is in ketosis, they are in a fasted state. There is no other way. To me, there are few better ways to define a fasted state than just measuring ketosis or not. If someone's in ketosis, they are fasted. Yes, I would submit that even if the person has actually consumed calories, if they're in ketosis, insulin and glucagon ratio is still reflective of a fasted state. They are still fasting, albeit perhaps a nutritional fast, not necessarily a caloric fast, if you can appreciate how I'm piecing those two apart. Now, all of this has been kind of a story of what the mitochondria are within the cell. Me, at least, introducing them as a main character here in this story. Now, how are the mitochondria regulated? And that's actually the meat of my talk. And I want to look at mitochondrial regulation in the context of these kind of two opposites, if you will. Now, I'm saying that they're opposites, and that's not entirely accurate. One is a peptide-based hormone in the form of insulin, and the other is a little carbon-based nutrient, as all nutrients are, ketones and insulin. But I'm presenting them as opposites in a way because You won't normally, physiologically, have both of them elevated at the same time. We can kind of beat that by now drinking ketones and eating a bagel at the same time, so they both could be elevated. That is not a natural state. Normally, ketones are up because insulin is low. Now, what I want to spend the remaining time talking about then is how these two characters, ketones and insulin, influence these three aspects of mitochondrial physiology. Mitochondrial number, the structure or the morphology, and then the actual degree to which mitochondria are working. And I'm going to define that more when we get there. Okay, now as a reminder, of course, as I mentioned earlier, we have to have healthy mitochondria to work. And then as a caveat, I mentioned here with insulin, we need normal insulin. Insulin is a necessary signaling molecule to the cell, and it even plays a role in normal mitochondrial physiology. So when I'm talking about insulin throughout the rest of my talk, I want you to be thinking about this hand-in-hand event of hyperinsulinemia and insulin resistance, which I'm not going to take the time to define. You, I suspect, all know it. So when I'm talking about insulin, I really mean to say hyperinsulinemia and insulin resistance, again, which goes hand in hand. I submit in every instance. Okay, first one, mitochondrial number. Hopefully you guys are doing all right and not getting too sleepy-eyed. Really, for me, the challenge as a professor is that I have to be provocative enough for my 2-hour lecture to keep the students off of Instagram. And I bet, you know what? I bet same thing's going for you guys. Some of you guys are flipping at Instagram, so put your frickin' phones away. What did you pay the concert for? You don't have a parent paying your tuition. You paid this yourself. Okay. All right, so with mitochondrial number, the main event to talk about is mitochondrial biogenesis. That's just the term for referring to the cell's ability to take what was, say, once one mitochondria and really start to expand the amount of mitochondria found within the cell. So that's mitochondrial biogenesis. And there's one primary key player, and that's this transcription factor, PGC1 alpha. PGC1 alpha is the key to promoting mitochondrial biogenesis. And Adam Nally mentioned thyroid hormone promoting mitochondria. In fact, it does it because of T3's effects on activating PGC1 alpha. As insulin climbs too high, insulin inhibits PGC1 alpha. So hyperinsulinemia starts to turn that transcription factor off, toning down the cell's ability to produce mitochondria. Now remember, when I'm focusing on mitochondria, you have to remember why it's relevant. And it's relevant for far beyond just ketogenesis, which understandably this group is interested in. We're all interested in ketones. And that, of course, requires mitochondria, as we'll get to. But please keep in mind the fact that the mitochondria are essential to normal cellular function. So hyperinsulinemia inhibits mitochondrial biogenesis via the inhibition of PGC1 alpha. We're turning it off. One thing that's kind of noteworthy about this is that earlier I mentioned that insulin is a main anabolic hormone. Yes, it is absolutely true. What's so interesting, those anabolic processes that I have mentioned there, lipogenesis, glycogenesis, and then even cholesterol synthesis, those are events that occur outside of the mitochondria. They occur in the cytosol. So the mitochondria, rather insulin, signaling anabolic processes, it doesn't need the mitochondria anyway. The mitochondria are involved in catabolism, as we'll come to in a bit. Now, I'm going to show just very briefly a little data from a paper we just published last year. And all those first authors are undergraduates. Remember, at BYU, undergraduates are remarkably productive. Whatever thing else you want to say about BYU, boy, these undergraduates they're something else. They're not goofing off. No spring break at BYU. They're in the lab. Okay, so what happens on a Saturday night? They go bowling for an hour and they get bored, and because no one goes to the bar, they go to the lab and get some experiments done. So here, we actually looked at what insulin was doing to mitochondrial function in fat tissue. And there's a lot more to this story, but I'm only going to show this, where we found in 2 different types of fat, not in the classic white fat, no effect on PGC1 alpha, it maintained normal levels. These are called Western blots, when we actually get a picture of how much protein is there, essentially. We found that in the subcutaneous adipose tissue, the adipose tissue of humans and rodents that can become brown, That's the type of fat that, of course, is right beneath the skin that can jiggle and be pinched. And or the actual brown fat, which in the animals is right between the scapula, and in the humans it's generally around the thoracic cavity and the collarbone. So here we see that PGC1 alpha in both instances, as we have it quantified in the figures, this one and this one, we see that there was a significant reduction in PGC1 alpha protein just by inducing hyperinsulinemia in the animals. And we aren't the only ones that show this. There's several other papers that find hyperinsulinemia or chronic exposure to insulin also will turn down this mitochondrial biogenesis. Now that's insulin. What about ketones? Ketones, in fact, have a very powerful activation of PGC1 alpha. So what was once one lonely little mitochondrion becomes the whole population of mitochondria within the cell. And that in and of itself isn't particularly surprising insofar as even for a cell to use the ketone, as I mentioned earlier, it must have mitochondria. The main catabolic processes, and in the case of ketone, the entirety of the catabolism of the ketone, ketolysis, occurs within the mitochondria. And that could be why multiple papers report this phenomenon, where ketones, beta-hydroxybutyrate in particular, induce mitochondrial biogenesis. And the activation of PGC1 alpha is a big part of that. So we wrap up this first concept, how insulin, hyperinsulinemia, and ketones influence mitochondrial number, whereas insulin resistance and hyperinsulinemia tends to have a dampening effect. It abhors the cell using the resources to produce more mitochondria. Remember that because mitochondria exist to break things down, but for the sake of the cell, of course, unlike my kids in the playroom, which break things down just to break things down. Here, the ketones are, in contrast, having a positive effect, activating mitochondrial biogenesis, if for no other reason than it has to have mitochondria, the ketones do, in order for the ketones to simply be used as an energy source. Next, with mitochondrial morphology. This is the classic way of presenting the mitochondria. When the previous speakers have shown it, any version, any time you see the mitochondria, it's always this kind of circular, kind of bean-shaped molecule, a little oblong. The reality is, I will never forget the first time we imaged mitochondria within muscle cells. I hope you can kind of see that. We stain it with a red dye called mitotracker, and what you can see, it's these long, little stringy things. That's the reality of mitochondria, at least when they're allowed to be dynamic, and they are very dynamic, moving around the cell, changing all the time. But what's relevant about even the name mitochondria is that mitos means thread. When you look at the mitochondria, they look like little threads. And so rather than looking at the mitochondria as a small little distinct ball or oblong shape, the reality is there are these big reticular structures connected throughout the cell. Now, however, they can exist in that very distinct shape. And so mitochondria, as I mentioned earlier, are very dynamic. They can flux between these two instances, or these two scenarios. And that's through these processes that we refer to as mitochondrial fission, which separates the mitochondria, pulls them into distinct little balls or globules, versus mitochondrial fusion, which has those little distinct globules start to come together. And again, it is dynamic. The cell is allowed, or it's expected, it expects to be able to flux between the two. In the case of hyperinsulinemia and insulin resistance, it gets the cell stuck in a state of fission. It promotes and locks in mitochondrial fission. The problem with this, and we published a paper about 4 years ago looking at some of this, when the mitochondria are stuck in fission, their ability to produce ATP is compromised, so less energy production for the cell. It promotes insulin resistance, exacerbating what was already causing the problem. It produces more reactive oxygen species, which we call oxidative stress, and it promotes fat gain, and that could just simply be a consequence of the insulin resistance and the compromised energy production. One cell type that is particularly susceptible to this event are neurons. And we see that within the nervous system, how insulin resistance is promoting this state of fission, in addition to the work that we published from my lab looking at muscle cells. Now back to this paradigm of displaying the mitochondria being dynamic, going through fission versus fusion. Ketones in fact, as you can already guess, have a different effect. Now, this has not long been known. This study mentioned that we really don't have a great deal of understanding on how, in this case, they're talking about ketogenic diet, but how ketones influence this mitochondrial dynamic, whether it's more fusion or fission. And so being a scientist, one of the great beauties, and I mean it, of being a scientist is we just get paid to ask questions. That's a wonderful thing, to be paid to be curious. And then we try to find a way to pay to answer your question. But we did this in cheap ways and in less cheap ways. But the first process was to just treat muscle cells in culture with beta-hydroxybutyrate, just supplementing the growth medium with the ketones. And then next step was putting the rodents into a ketogenic diet. And I will never forget when the first time I ever met Amber, or her mentioning to me this advantage of humans being able to get into ketosis quite readily. And I didn't even really appreciate it. And yet, in hindsight, look back and realize what you have to do to get a rodent into ketosis, other than fasting, which works, is 1% carbohydrate diet. Yeah, it's pretty remarkable. That's what I mean. That's reflected there. The macros have to be extraordinarily low carb to put a rodent, in this case a rat, into ketosis without fasting them. So that was the model that we used. Now, this was a study we published just last year. Once again, an undergraduate who's actually at medical school here at the U, a remarkable student, once again, has nothing else to do on a Saturday night, so come into the lab and get some work done. So what we found in treating the muscle cells with ketones, well, firstly, to lay out the experiments, it was in fact very, very simple. And we did this, we always start with cells to try to get proof of concept, because it's so cheap to do. We just try to get proof of concept in the cells, and then we kind of graduate the project to the more expensive model, which will usually be rodent and then maybe human at the end. So in this case, treating the cells with BHB versus normal glucose-rich medium, we found a significant difference in the expression of two relevant proteins, mitofusin 2, which promotes fusion, and then a protein, dynein-related protein, DRP1, which promotes fission. And you see here, the general trend is that there's a greater expression of mitofusin 2. That was quite obvious. And then more subtle, because of the variety here, but a general trend, well, this was beyond trend. This was very significant. This was a trend of a reduction in DRP1. And then we actually quantified the amount of fission versus fusion via confocal microscopy. Again, we put on a dye that will fluoresce when it hits the mitochondria. Then we can get pictures of that under these very high-powered microscopes, confocal microscope. We got those images, and then we had a student who laboriously actually took those fields and then quantified the degree to which there was fusion versus fission. And you can see that in the cells treated with beta-hydroxybutyrate, the black bar dropped significantly, and there was much less fission, much more fusion. But still both present, which you need. And in the rodent aspect of this study, we simply put them on the ketogenic diet or the standard lab chow. From muscle, this was gastrocnemius, which is a mixed muscle. It has both fast twitch and slow twitch, and I bet you guys have heard of those before. We see here much more mitofusin 2, and no insignificant differences with DRP1. But nevertheless, still suggesting this overall scenario where fusion is enhanced in muscle. So to wrap this topic up then, with mitochondrial morphology, hyperinsulinemia and insulin resistance is promoting this state of distinct, separate, dysfunctional mitochondria. Not to say that fission is bad, but the hyperinsulinemia is locking in the fission. It's a forced and sustained mitochondrial fission that is in fact pathogenic. Whereas ketones are allowing this mitochondria to maintain this dynamic effect and in particular have fusion occurring. Now lastly, mitochondrial function. I'm going to define mitochondrial function as oxidative stress, so the production or the defense against reactive oxygen species, and then coupling status, mitochondrial coupling versus uncoupling. Coupling status sounds like something else we could be talking about at BYU insofar as so many couples get engaged and need marital advice. I'm not talking about that kind of coupling here. So with oxidative stress, we will, again, as I mentioned, we'll split this up into two subtopics. the production of reactive oxygen species, that's the ROS, and the efficacy or presence or amount of antioxidant enzymes. Now, as mentioned, I think Amy mentioned, we have to have oxidative stress. It is absolutely essential to normal cellular survival. It's essential to normal immune function. One of the main mechanisms a phagocyte, like the macrophage, can kill a pathogen is by doing something called an oxidative burst. It basically just blasts the pathogen to smithereens with this production of reactive oxygen species. So thank heavens for oxidative stress. We need it. The system was designed to have it there. However, of course, it can go too far. Now, when I'm talking about the production of reactive oxygen species, it essentially happens at the same level where we're producing ATP, which of course is the consequence of catabolic reactions and of course is necessary for anabolic processes. So here, rather than producing ATP, the cell ends up using the oxygen to produce the very first of the reactive oxygen species, the superoxide radical. I'm losing some of you as I see nodding up. And I don't have a way to spice it up. This topic is just heavy. I'm not going to apologize for it. So wake up, for heaven's sake. Okay, so anyway, here we have the production of the reactive oxygen species. And because too much isn't good, for these reasons here, we have mechanisms in place to deal with them, to squelch these reactive oxygen species. So that's this, kind of the Pac-Man eating up these reactive oxygen species, dealing with the oxidative stress. And of course, we need that. We need the balance here. So let's look at what happens when insulin is elevated. Suffice it to say, oxidative stress itself gets worse. The insulin resistance itself can drive the oxidative stress. In fact, it can also go back around full circle. Oxidative stress is known. You can induce oxidative stress in insulin-sensitive cells, and every cell is, in fact. But that you can create insulin resistance in that case as well. But let's look firstly at the production of the reactive oxygen species themselves. This was a very neat study. They took these cells and they had elevated levels going up and higher levels of insulin, treated with these levels of insulin over time. This is in minutes. So just in 1 hour, and looking at the production of reactive oxygen species, and the hotter the cells are, the more they're fluorescing, in this case with the green fluorescence, the more they're producing reactive oxygen species. In other words, the greener the cells are, the more oxidative stress they're experiencing. And you can see, look at this spike in oxidative stress. And these are pretty physiological doses, well, a little elevated on this end, but that's still the insulin, the chronic, well, not chronic, 40 minutes for heaven's sakes, exposure to insulin was significantly increasing the oxidative stress. Now, on the antioxidant side of things, the main enzymes, I'm not going to take the time, here are just the key players that are considered antioxidant enzymes, or are, within the cell. So these are the molecules that are trying to deal with it. Multiple studies suggest that insulin resistance hyperinsulinemia is reducing the presence and the efficacy of antioxidant enzymes. And the general theme when we start to increase ketones is the opposite, not surprisingly. And more evidence from our study that I just mentioned from last year, we found in muscle cells, we actually looked at after the cell has made the oxygen radical, that was the O2 minus that I showed you a second ago, the way the cell deals with it is to turn it into H2O2. Yes, the very hydrogen peroxide we're putting on our little scrapes. It's because it kills the stuff that's trying to get into the body. It also can kill our own cells if it gets too high. So we looked at how much H2O2 are muscle cells producing as it's consuming oxygen. In other words, how much of the oxygen the cell is consuming is being used to just simply turn into H2O2. And you can see when the muscle cells were fed beta-hydroxybutyrate, as opposed to strictly glucose, a significant reduction. It was a p-value of about 0.01, less than 0.01. So a very significant reduction in the production of H2O2 per oxygen consumed. In other words, the muscle cell is cleaner with the oxygen that it's taking in and using. It's producing less of this bad exhaust in the form of H2O2. And more studies here. Now, in looking on the antioxidant side of things, the degree to which ketones are influencing these enzymes that try to keep oxidative stress in check, one of the main one is the glutathione peroxidase. this middle enzyme. And indeed, ketones have long been known to increase among all of those glutathione peroxidase increases. So presenting a very effective way for a cell to deal with oxidative stress. I've spoken, in fact, the very first talk I ever gave in the realm of in the low-carb community was looking at how ketones and insulin affect coupling. And when I talk about coupling, what I mean by that is the degree to which, here's this paradigm again, the catabolic processes are either producing ATP, and in that case, it's coupled. In other words, you're only using as much nutrients, you're only breaking down as much lipid and glucose, for example, as you need energy. So basically the cell is saying, all right, I need this much ATP, I'm going to use that much glucose and lipid for fuel. In contrast, you can separate that process. And now you're chewing through, say, lipid and glucose, but it's uncoupled. It's not because you need energy in the form of ATP. You're just chewing through for no good reason. In other words, it's creating heat. That is mitochondria that are more uncoupled, or mitochondrial uncoupling. Now, this event occurs here along the intermitochondrial membrane through the electron transport system, and I'm not going to get into that. But both of these instances can be useful. Uncoupled mitochondria, that's good if you want to just waste energy, like if you have too much energy in the form of too much body fat, that would be very helpful. ATP, and it's more tightly coupled, like at the muscle cell. You want it to be very tightly coupled because then the muscle's never wasting energy. It's only using the lipid and the glucose to make the energy that the muscle needs. So it's pretty smart. Now, which process is better? Uncoupled or coupled? Well, it really just depends. And then let's look at the big overview version of what I've been spending the last 4 years studying. So it pains me to cover this so quickly, because it's been so painful to answer all these questions. But for you, I'm going to give you the Cliff Notes version. Insulin is making the fat cells be more tightly coupled. It is telling fat cells, don't waste energy. And this is reflected in that paper that I showed you earlier that we published last year, and more to come in the context of, in the case of ketones, very, very soon. Whereas insulin appears to have no general effect on coupling or uncoupling at the muscle cell at all. The muscle just continues to work as normal. Overall, though, this is promoting a general situation in the body where insulin is telling the body to store energy, don't waste it. Remember, insulin abhors wasting. Now, ketones, this is what we're doing again in the lab actively. There's no effect, that was the paper we just published. Ketones have no effect on mitochondrial coupling or uncoupling. They maintain perfect efficiency, muscle cells do when they're fueled with ketones. And in fact, they're better because they're producing less oxidative stress. And then when you look at the adipocytes, they're more uncoupled. And this is the research we're doing actively, where ketones are promoting the uncoupling, allowing the cells to waste energy. We have gotten now to the point of human research. So we have humans coming in normal non-ketosis states versus ketosis states, and we do two things. We put them under this big space helmet and measure their resting energy expenditure, basically their resting metabolic rate. And then we pull a little piece of fat from right beside their belly button and we numb it with a teeny bit of lidocaine, and indeed that is the worst part, I can tell you from experience. I was the first subject for this very procedure because we'd never done it before, so we did it on me. And that's what you can do, right, in science. Whatever you want. Not quite. As long as you have IRB and ICAR approval. So we numb it with lidocaine, and then we make a little incision and then use a hollow little needle and pop out a piece of fat, and then we measure the mitochondrial function. So let's look firstly at the adipose biopsy. We saw immediately the people that are in ketosis have significantly higher metabolic rates, and that's basically what we're looking at here. They're using much more oxygen. That means they're busier. ATP production tended to go down, a trend, but when we looked at the amount of ATP or phosphorylation, P to oxygen used, O, the P to O ratio, we found that these cells were making much less ATP as they were consuming the same amount of oxygen. Or if we said these are consuming the same amount of oxygen, they're making much less energy out of it. In other words, the fat has become significantly more uncoupled. So the fat tissue from people in ketosis is wasting energy to create heat. Pretty interesting adaptation. And in fact, even cold exposure can increase ketogenesis, and it could be because the ketones then activate the fat to become hot. When we looked at resting energy expenditure, we found no significant difference across the group in general. However, when we split it up among those college-aged kids, and then those of us that are not college-aged kids, we saw a slight, it is always slight, but a significant difference. The older people that were in ketosis had higher metabolic rates, indeed not significantly different from those young college kids. We basically were bringing metabolic rate back up to that higher level. Take that, 20-year-old. Okay, so in summary, yeah, thanks for staying awake. You guys have really been troopers here. If we look at what mitochondria are doing, as insulin tries to have its way with the mitochondria, and ketones try to have their way with the mitochondria, first, the conclusion was that insulin is reducing mitochondrial biogenesis. It does not want the cell to expend that kind of energy. Ketones, in contrast, are promoting mitochondrial biogenesis, if for no other reason than it needs the mitochondria in order for the ketones to be catabolized and be useful at all, for the sake of energy, at least. The second, in hyperinsulinemia, is promoting and sustaining, that's important, sustained mitochondrial fission. It's not allowing the mitochondria to be dynamic anymore, whereas the ketones are just generally promoting fusion, which is enhancing ATP production, for example. And then lastly, with regards to mitochondrial function, I'm just generally saying the hyperinsulinemia, it's disrupting the mitochondria. More oxidative stress, compromised ability to enhance production of reactive oxygen species, compromised ability to deal with those reactive oxygen species. And in contrast, when fueled or exposed to ketones, the mitochondria within the cell appear to be working a little better. Reduced oxidative stress, enhanced ATP production, and this kind of odd, unique differential effect where you have uncoupling of the adipose tissue or the fat tissue, and yet perfectly maintained coupling at the muscle cell. So a pretty fascinating and almost intuitive event. That's it, and I look forward to any questions, any at all. Thank you.